Okay, so good morning. So this is my last lecture. So today I'd like to discuss other Swampland conditions. And as I said in my first lecture, there are various landscape of Swampland conditions. And so I have organized the Swampland conditions in two scales: the useful to useless, and rigorous and speculative. And for the last three lectures, I have discussed the one on the top, which is something that we can prove, at least in the context of ADS-CFT correspondence. And so I showed that in the context of ADS-CFT correspondence, it is not possible for quantum theory of gravity to have global symmetry in a way that I defined. And with respect to that global symmetry, but then you cannot have global symmetry, but you can have local gauge symmetry in the bulk, which appear as global symmetry of the dual conformal field theory. And with respect to that gauge symmetry, it has been speculated and conjectured by Polchinski and others that all possible charges should appear, that all finite dimensional unitary representation of a given gauge group should appear in the spectrum. And so it's called completeness hypothesis, which I was also able to give proof of. So now today I'm going to go down this the rigorous speculative scale and then discuss some of the speculative conjecture which become more useful in the sense that I'm going to talk about today. So so we'll talk about distance conjecture, weak gravity conjecture. Since Nima is not here, so I put the weak gravity conjecture on the slightly on the useless side of the conjecture. So these are conjectured in 2006. And so there is even more speculative conjecture that we'll discuss. So this was conjectured in 2016. And then there was some follow-up development, and then this was conjectured last year. And there are various logical connections between them, which I hope to exhibit. And I want to make sure that how much we know and how much we don't know, and so that we can sort of use some of these conjecture with grain of salt. And there are various logical connection and also some mutual relation between them, which I would like to exhibit. So let me first discuss distance conjecture. It is over here, and I'd like to explain why I put this in a scale that is more useful but less rigorous. It is less rigorous because we don't have such a derivation as the one for no global symmetry. It's mostly based on example that we know from string theory. At least that was the way that we conjectured in 2006. So in many string theory compactifications, in particular the supersymmetric one, they often have moduli space. This is a space of expectation value of massless scalar field that emerge in low energy. And there are many things that we can say about this moduli space. And so the class of conjecture, the general property that we can infer from known example, we have summarized it in the class of distance conjecture. First thing is that string theory has no free parameters. But of course, this was known many years ago, and this is one of the most attractive aspects of string theory, that all the parameters in string theories are expectation value of some scalar field. So you can think of moduli space also as a space of parameters of low energy theory. And the kinetic term of this scalar field specifies the metric on this space. So the metric on M is given by kinetic term. One of the interesting property of this moduli space that we observed is that M is non-compact. That is that there is a direction where you can go infinite distance from given point. So if I write it more mathematically, it means that for any point on this moduli space, and for any large positive number that you can consider, you can always find another point in moduli space where the distance between that point and the original point exceed this arbitrary set distance. So that means that you can start from P and you can go arbitrary distance staying within the moduli space. You can go any distance. And so that is a very interesting property. And nevertheless, typically moduli space has finite volume with respect to this metric. So that means that the moduli space has this kind of structure where you have sort of very thin tentacles extending to infinity on the moduli space. Another conjecture has to do with how this non-compact, what kind of physics control this non-compact direction. And what we can observe is that typically if you go infinite distance in this direction, the low energy effective theory breaks down. By that I mean the following. So when you are sitting somewhere in the middle of the moduli space, then you have some low energy effective theory describing physics around it, which typically is described in terms of Einstein gravity coupled to some finite number of matter field, which is scalar field and gauge field and sum of fermions. But what happens when you go infinite distance in any one of these directions? New light degrees of freedom start emerging, which you have not included in the low energy effective theory. So you have to revise low energy effective theory. So you can quantify this in the following way, that compared to the low energy effective theory, LET is the low energy effective theory at P0, the low energy effective theory at P with distance greater than T has a tower of massless particle. And the mass goes exponentially small with respect to distance. So as you go in this infinite distance from the given point, the very light degrees of freedom start descending and breaking low energy effective action. So what happens is that if you go all the Planck length, Planck mass size scale distant from this original position, then low energy effective theory would break down. So this is in this diagram of landscape of Swampland condition, I put this distance conjecture more useful than the conjecture that we have, the theorem that we have proven in the last two lectures, because it gives you more quantitative prediction of how the Swampland condition works. What are the conditions for quantum theory of gravity? So in the case of no global symmetry theorem that I proved, we say that whatever accidental symmetry you have in low energy cannot be upgraded to full exact symmetry of quantum theory of gravity, but we cannot say how and when this symmetry can be broken. It can be broken by dimension 5 operators, 6 operators, or non-perturbatively, or it can actually be gauge symmetry in disguise. We don't know. But for distance conjecture, we have more specific claim that moduli space is non-compact, you can go infinite distance, and whichever direction you go, you start getting light degrees of particles, and then low energy effective theory breaks down. So this is a very specific conjecture. We also have a conjecture that the moduli space is essentially simply connected. And well, in view of time, I do not have time to go too much detail. But if you have a moduli space has this non-compact direction, but you can consider closure of the moduli space. And if you consider closure of moduli space, which I denote by m bar, then this is trivial. And this is again true in any known example. So typically, the moduli space has a structure that you have a universal covering of the moduli space and divided by some discrete group, gamma. And this gamma has fixed point. So that means that in a case like that, when the Teichmüller, you can call this as Teichmüller space, is simply connected, then the pi 1 of closure of M is given by the discrete group gamma itself. And each gamma has a fixed point. So that means that each of these non-trivial cycles can collapse to this fixed point. Okay? So typically, that is where the symmetry gets enhanced. So this seems to be the sort of common feature of non-string theory compactification. And we put forward this conjecture in 2006, as I said, based on examples. So let me describe some of the examples. So the first obvious example one can think of is the type 2A string theory, which is M theory on R10 times S1 of radius R. So let me use small r for the radius. So now, in this case, the moduli space is one-dimensional, the space of R, the radius, or the dilaton of type 2A string theory. And the metric on this moduli space is dr square over r square that you can calculate from kinetic term of the dilaton. And so therefore, the distance between 2 points on the moduli space with two radii of the circle is given by log of r over r naught. So you can see that there are two limits in the moduli space of infinite distance. One is r goes to infinity, and the other is r goes to 0. So r goes to infinity is a decompactification limit of the M theory, where Karuta-Klein particle appears. So you see that there is always right degrees of freedom. But you have to be a little bit careful, because when we make this kind of conjecture, we are making this conjecture for quantum theory gravity, so we have to keep the Planck mass scale finite. And we have to keep Planck mass scale of the theory finite. So if you compactify M theory on circle, then you have 11-dimensional Planck scale. And then there is a 10-dimensional Planck scale, which is related to a 10-dimensional Planck scale in terms of the radius. So the way to think about it is that you have Einstein action in 11 dimension, which you integrate, and you have integration over R10 and over S1. And the integration over S1 gives rise to the factor of radius, and that becomes Einstein kinetic term, Einstein-Hilbert term in 10 dimensions. So this relation relates 11-dimensional Planck scale to 10-dimensional Planck scale. So it is 10-dimensional Planck scale that you need to keep finite. And so if you work through the math, then you find that the Karuta-Klein scale goes like exponential of -9/8 of distance. So this fraction comes so that by requiring that the 10-dimensional Planck scale is kept finite. So I leave it to your exercise to figure to derive this fraction. It's a good exercise to do. But anyway, so you indeed reproduce this. So similarly, r goes to 0. So naively, r goes to 0 does not seem to be infinite distance because you can just shrink the size to be 0. But according to this metric, it's actually infinite distance. And moreover, there is a right degrees of freedom coming in. And you can calculate this right degrees of freedom. And then you have 3/8 of the distance. You can ask, what kind of right degrees of freedom can you have in type 2 string theory? So r goes to 0 is a weak coupling limit. So what kind of right degrees of freedom can you have in the weak coupling limit of type 2 string? Any Any suggestion? You have type 2 string, you have no interaction, you are turning off the interaction of type 2 string, and I'm saying that there is a tower of right degrees of freedom. What are they? These are just string excitations. So type 2 string has a tower of string excitations. And of course, these are organized according to the string mass scale. But we are taking the 10-dimensional Planck scale finite. And if you take 10-dimensional Planck scale finite and take the zero coupling constant limit, then what happens is that you can do the math, you can work out the math. You can write 10-dimensional Planck scale to be equal to g to the g to 1/8, I believe, of minus 1/8 of the 10-dimensional string scale. So if you take the g string to be 0, and if we want 10-dimensional Planck scale to be finite, then you need to take 10-dimensional string scale to go to 0. So in fact, if you if you take 10-dimensional Planck mass finite, go to weak string coupling limit, there is a tower of massive particle coming down, and these are nothing but the stringy excitations. So this is again consistent with the distance conjecture. And there are other conjectures you can derive. If I have eraser, I can, maybe that it's down here, so let me, oops. Yeah. There are other situations. For example, you can compactify it, string theory, type 2B string on K3 surface and ask whether this conjecture is true or not. So you can have 2B on R6 times K3. So in this case, the moduli space, this is supersymmetric, and the moduli space is a coset space. And there are various directions of infinite distance, typically the fixed point of these discrete groups. And you can show that each one of infinite distance point is actually dual to decompactification of K3. So one of these moduli space, one of the parameters of the moduli space is, of course, the size, the radius of K3. So if you take the radius of the K3 to be infinite, the Karuza-Klein mode comes down just like this one, and you have a tower of light particles. But you can show that every one of the infinite distance direction is like that, dual to that. So again, there is a tower of light degrees of freedom. So this is for K3 compactification, but by now there have been extensive study of R4 times Calabiar, for example, Timo and Wolfgang may have looked into that also. And there is actually, this conjecture has been extensively studied in a more complicated moduli space. There has been very interesting works understanding various logical issues, logical connection of this conjecture with other things. So for example, I said two things in this conjecture. One was that there is always infinite distance direction, and the other is that if you go infinite distance, then light degrees of freedom comes down. It seems like there is actually a connection between these two facts. That the very fact that the light degrees of freedom is coming down is causing the distance to go to infinity. So this has been actually discussed suggested by various people, that if the light degrees of freedom start coming down, it affects your the kinetic term of the original massless particle, because clearly these particles couple to this massless particle through the dependence of the mass, and then this causes the loop effect of this light. If the particle starts coming down, then the quantum effect becomes relevant, and it's going to modify the kinetic term, and this causes the metric to go to infinity. So there has been various suggestions like that. You are raising hand.
Could you just explain the notation there? Is it a quotient space on both sides?
Yeah. So there is a. So this is a continuous quotient. So you can think of this as a quotient coset space, and then there is a still discrete group acting on this that you are dividing it. Okay. Now there has been some work in the case without supersymmetry. This is harder to study, and typically non-supersymmetric case the potentials are generated. So there has been some discussion of exactly how to formulate distance conjecture in the case with potential. And as far as I know, there has not been complete consensus within literature about exactly how to formulate distance conjecture with potential. This is, of course, extremely important issue. So, for example, if we want to apply distance conjecture to various models of inflation, you want to know whether when you have inflaton potential, is distance conjecture still true that can you prohibit inflaton from traveling to Planck scale or higher without modifying the low energy effective action? So this is a very important question for inflation. And as far as that, so there are various evidences that something like that works, something like distance conjecture works with potential, but I think this is still work in progress. And but want to also mention that this is actually, as I said, this is known. This has been tested in all known cases that you can derive from string theory. It would be very interesting if you can come up with counterexample. I challenge any one of you to try to do that. But it's extremely so therefore it is extremely hard to come up with counterexample with gravity. And surprisingly, it is exceedingly easy to come up with a counterexample if the gravity is absent. So it's actually absolutely false without gravity. So you can pick almost any one of the non-gravitational system with a moduli space, and this is false. So for example, the simplest one would be n equal 4 super Yang mirrors in 4 dimensions. So in this theory, you have 6 scalar field, and you can give Bev to this, and you can go to Coulomb branch. And the Coulomb branch is non-compact. You can go to infinite distance, and nothing happens. Low energy effectivity theory is fine. The particle becomes more and more massive, and no light degrees of freedom comes down. So none of the distance conjecture is true in this case. Okay. So this is about distance conjecture. Any question? Okay. So there is another conjecture which was proposed in the same year, 2006, by Nima and collaborators, the weak gravity conjecture. And again, this is a more useful conjecture than the theorem that I proved in the last 3 lectures. And but on the other hand, it's less rigorous. And in some sense, both distance conjecture and weak gravity conjectures are refinement, strengthening of this no global symmetry conjecture. So distance conjecture is in some sense refinement in the following sense, that if you have light degrees of freedom, then there is a shift symmetry to the direction of light degree. If there is a massless, exactly massless particle, the moduli space, then there is a shift symmetry in the direction of the moduli space. And so that means that you can think of this as spontaneous breaking of symmetry. That there is a shift symmetry, and the symmetry is spontaneously broken because scalar field get vacuum excitation value. Our proof that there is no global symmetry works even when shift symmetry exists. So therefore, the distance conjecture, in particular the breaking of low energy effective theory, that if you go in a particular distance, necessarily physics should change. So that therefore the translational invariance in that direction should be broken. So sort of quantification of this no global symmetry theorem. No global symmetry theorem says that there is no spontaneous symmetry breaking exact, or spontaneous breaking of exact symmetry. So that means that if you go in infinite distance, something must happen. But this tells you quantitatively what happens in that direction. So it is, in that sense, it's a refinement. Do you have a question?
Yes, sorry. Did you mention that the distance conjecture also claims that the moduli space should be simply connected?
I did mention that.
Yeah. Is there an is this also a fact that's only true in quantum gravity, or can you come up with counterexamples in theories with
I think so. Yeah. I can easily come up with an example. You can have low energy effective theory whose scalar fields are taking value on cylinder, for example.
I see.
Yeah, so there is nothing wrong with this. Yeah, you can easily find. For example, we can just write down Maxwell scalar theory, whose scalar field take value on cylinder. So there is nothing wrong with this, right? So weak gravity is also refinement, and I briefly mentioned that in one of the lectures, that you can have a gauge coupling constant, and if you take the limit when gauge coupling constant goes to 0, then it becomes no global symmetry statement. But I have not told you what weak gravity conjecture is, so let me first formulate what weak gravity conjecture is. So suppose there is a low energy effective action, the low energy effective theory, which contains Einstein gravity coupled to some Maxwell field and some other charged particles. Then the weak gravity conjecture state that in the case like that, there is some particle. In fact, more generally, there is some state for which with mass m and charge q, such that mass is less than or equal to absolute value of charge normalized by the Newton constant, or maybe I can use 10-dimension the Planck mass scale, so you can write it as mp times the absolute value of the charge. There is actually precise numerical coefficient I can put, which I will discuss later. But this is a conjecture that was originally proposed, and there is no derivation. This is motivated by various facts and also some argument. The original argument is that somehow you would like extremal charged black hole to decay. That if you have a low energy effective theory which has Einstein gravity and Maxwell field, then you can consider rational Nordstrom black hole as a solution to this theory. And you can in particular consider extremal limit. And the extremal black hole has 0 Hawking temperature. So this is naively stable. And then this leads to some puzzle. I'm not sure whether it's a paradox or contradiction, but some people are uncomfortable with this. And so in order to avoid this problem, if you have a particle or state satisfying this inequality, especially the stronger inequality, then Hawking radiation can create such particle and decay and losing charge. So therefore, getting back to non-extremal situation. So that's one motivation. Another motivation, which I think is stronger, is that this is true in any non-string theory compactification. So again, we can go through some example, but in view of time, I will skip it. So this has also been tested in many ways, and I will give you some example. But so this is a very interesting and useful conjecture, 2006. But ever since this conjecture was put forward, there was always a question of why we have this equality here. So can we get rid of this equality? Well, one of the reasons that we have equality here is that if you have a supersymmetric theory, and in particular a theory with R symmetry, and if you have a gauge field coupled to this R symmetry, then you can have BPS particle, and BPS particle has equality. So therefore, you would like to include that. But we do not know of any other example other than a case with supported by BPS particle, where this equality is exactly satisfied. So this led me and Kumran to conjecture in 2016 that there is a stronger conjecture that you always have a particle whose mass is strictly less than the charge. Oh, by the way, I forgot to say, I got to explain why this is called the weak gravity conjecture. The reason it is called the weak gravity conjecture is that if you have a such particle, then you have a particle with mass, so there is a Newton attraction between pair of such particle. But you have also Coulomb repulsion between pair of such particle. And if this inequality holds, then Coulomb repulsion is stronger than Newton attraction. So that's why it's called weak gravity conjecture. That there is at least one particle in the spectrum where Coulomb force is stronger. Yes, you have a question.
So to be precise, you're saying there must, in the stronger version, there must at least be one particle that...
Yes, the original conjecture is that. Yes.
But
now there are stronger conjecture these days about lattice conjectures, etc. Yes.
No, but about the BPS property. So you say as long as there must be at least one particle that strictly satisfies the equality, but in addition there could be other non-BPS states that satisfy.
Yeah, but if you have supersymmetric case, then you cannot have particle which violate BPS bound, right? Yeah, so for BP, so for in the case of R symmetry, therefore, this has to be satisfied, not this one. This would violate BPS bound. Okay, so let me describe evidence for it. So the first evidence, actually, this was pointed out by Katz, Rubos Motor, and Paddy in the same year. And this is a very interesting work, and it's closely related to actually what Nima was talking yesterday, which has to do with the positivity of higher derivative terms. So suppose you have low energy effective theory with Einstein gravity coupled to Maxwell field and other field. And you can compute, you can construct a rational Northstone black hole. So we know that you have for each mass and charge, you can construct you can construct the rational Northstone black hole. And in particular, if you have extremal rational Northstone black hole, then its mass is given by Planck mass times the charge. So this is the extremal. So if I sort of draw a diagram, and then here is a charge, and here is the mass of the black hole, then for large mass and charge, you have this straight line. And all allowed particles has mass greater than this, so you are in, so these are allowed region. And then there is a straight line going in this direction. Okay? So this is an extremal black hole, these are non-extremal black hole. But this is true for large mass black hole, because for small, if you try to reduce the mass, then it's possible that some of the higher derivative term become relevant. You can have R squared term, or you can have f to the fourth term, etc. And those higher derivative terms can become relevant. And this higher derivative term can start modifying this extremality condition. So this line can either go this direction or this direction. Okay? So we don't know. So it turns out that there are actually positivity of these coefficients. And Ubos and the collaborator checked various examples of string theory compactification, heterotic string on Calabi-Yau, etc., torus, I guess. And they found that there are actually positivity conditions for these coefficients. And it is so that this extremal black hole formula is modified to be like this, where epsilon q is positive. So what in fact happens is that it actually curves in this direction. So that means that you can actually create a state which satisfies this inequality. It's not a particle in this case. It just turned out to be extremal black hole, which is smaller than this asymptotic region. Okay, so this is a sign. This shows that in this particular case, weak gravity conjecture is indeed satisfied because you can choose any one of these black hole states as a required state. Now, it's an interesting question whether you can derive this from unitarity constraint or causality constraint that Nima was talking about. There are various sort of suggestions that something like that is true because there are close relation between positivity that they considered and positivity that one can derive from that, but doesn't quite, as far as I know, they don't quite match up. So it's still a very interesting question.
I'll say something about it at the end of my lecture.
Thank you, thank you. And then the other thing is that this shows that weak gravity conjecture is realized, but this is not necessary. So you don't have to have this because it could have been that it went this way. It could have been that it went this way, but there could have been particle here, for example, and then that would have satisfied it. So we didn't have to we didn't need it, but it turns out that it happens in known example in string theory. So that's very interesting. So this is the case when the weak gravity conjecture is satisfied by smaller black holes. But there are other situations. So for example, you can consider heterotic string on torus. So if we have a heterotic string in torus, then the perturbative string states are classified by the lattice of momentum and winding number, which is given by a point on the lattice. And the mass of the stringy state is given by 1/2 of p left square plus n left minus 1, which is equal by the level matching conditions. Yesterday at the speaker dinner, there was a suggestion question of how many of you have gone through quantization of perturbative string theory. And are you familiar with this formula? No? Some of you are shaking your heads. Okay, okay, so there is something that the advisor have to work on. So important thing is that this contains both BPS particles and non-BPS particles. So in this case, actually, supersymmetry acts on the right moving sector. And if you have stringy excitation in right moving sector, supersymmetry is broken for that sector. And supersymmetry particle satisfies the preserves fraction of supersymmetry if right moving excitation is 0. So in this case, you see that mass of the particle is related to 1 over square root of the size of the right moving momentum. And in fact, here I'm setting string scale to be 1 or something, so that it doesn't look quite that, but in fact, you see mass is proportional to charge, and this is exactly this weak gravity condition. And in this case, the weak gravity condition is saturated because it's a BPS particle. So this is actually related to the R symmetry, R charge of that particle. So weak gravity conjecture is exactly saturated in this case. But how about the non-BPS particle? So you can have a situation where right moving string is excited, but left moving string can be at ground state. So suppose you have such a situation. So NL is 0, but NR is non-zero. So in this case, the particle does not preserve any of the supersymmetry, so it is non-BPS. In this case, mass is given by 1 over square root of square root of 1/2. I'm sorry. The mass is given by 1/2 of p left square minus 1 inside of the square root. So this is less than 1 over square root of absolute value of p left. So you see now the inequality is strict, that there is that you actually don't saturate the bound, and so non-BPS particle case, the inequality is satisfied. So this is sort of an example which demonstrates the strict weak gravity conjecture. Let me give you one more example. So this actually specifies the coefficient. So you can actually specify the coefficient precisely because this inequality is given by the extremality condition of rational norms on black holes. So you can work out the coefficient. And it was shown by Heidenreich, Rees, and Ruders that the coefficients given by this. So this is actually more precise formula for weak gravity conjecture. So this is given by gravitational theory in d dimensions. Now suppose you start with d dimension and compactify down one dimension lower by compactifying it on circle. Then this coefficient changes. But you have this particle in higher dimension, so you have to have that particle in lower dimension. So you can ask whether that particle satisfies the weak gravity conjecture or not. And the interesting thing is that d minus 3 over d minus 2 is greater than d minus 4 over d minus 3. So that means that this coefficient becomes smaller when you go down the dimension. But it turns out that in the supersymmetric compactification, I forgot to say what alpha is. Alpha is a Diraton coupling. So in the supersymmetric case, if you compactify it, you have to actually change the Diraton to go to Einstein metric, Einstein frame. So their alpha is changed in such a way that actually this coefficient stays fixed. And therefore, weak gravity conjecture is satisfied by the same particle. But typically, when you break supersymmetry, all the scalar field gets potential, and the Diraton coupling cannot be adjusted by compactification. So that means that this is constant. So in that case, what happens is that if you go down the dimension, this coefficient becomes smaller. So in that case, what happens is that if you have a particle which satisfies the weak gravity conjecture in higher dimension, if you compactify it, break supersymmetry, then you would expect that strict version of weak gravity conjecture be satisfied. So this is yet another example that the strict, in non-supersymmetric case, weak gravity conjecture can be strengthened. So based on this argument, Kumran and I speculated 2 years ago that there has to be some strengthening. But this leads to a rather surprising statement. Because, by the way, this can be generalized to brane also. So if you have higher forms field, P-form field, then there is a brane coupled to it. And if you have a brane coupled to it, you can actually formulate weak gravity conjecture, and then it leads to the same kind of argument. So this leads to our further conjecture, which I described in this useless diagram, that there is no construction. You cannot have ADS geometry which breaks supersymmetry. So here is an argument. So at least almost all known construction of anti-Lita space is based on flux compactification. So you have some higher dimension, higher form field, and it has flux, and its expectation value contribute to the negative cosmological constant and give rise to ADS. So that's sort of typical construction that you have in anti-Lita space. But if you have this kind of, and then typically this form has to be maximum. Maximum dimension, so P has to match with the dimension of ADS, so that ADS isometry has to be satisfied. So if you have such P form, then there must be brane that coupled to that P form, and if that P form saturates and in fact satisfy the weak gravity bound, then what happens is that nucleation of that P form makes the ADS space unstable. So this is very similar to Schrödinger pair production. So in the case of Schrödinger pair production, what happens is that if you have electric field, you have constant electric field, then you can actually simultaneously create electron and positron. And if the distance between electron and positron is sufficiently large, the electric potential pays for the cost of creating the pair of particles. So then the vacuum starts creating this pair of electrons and positrons, and the electric field gets neutralized. You can have similar mechanism for anti-Lita space without supersymmetric. So that's what Qumran and I conjectured. And namely that any non-supersymmetric ADS should become unstable either by the stability of some of the scalar field or the nucleation of the brane induced by flux in the space. And in fact, something like that is known to happen in many examples. So when the first ADS-CFT correspondence was proposed by Mardo-Senna, Shamit-Kachru and Eva Silverstein came up with a very ingenious construction which generalized this in non-supersymmetric case. Their idea was to divide this S5 by some discrete group, and then divide the R symmetry of super-ion mirrors by the same discrete group. So because of the ADS-CFT correspondence, there must also be such correspondence in non-supersymmetric case. And you can show that you have non-supersymmetric case when gamma does not fit within the SU3 subgroup of SU4. So this was constructed in 1998, immediately after ADS-CFT correspondence. It turns out that this construction does not exist. It's unstable. And what happens is that there are cases when this gamma has S5 has a fixed point with respect to gamma. In that case, at that fixed point, the tachyon, which breaks the Breinton-Friedman bond, emerge, and then it becomes unstable. When this has no fixed point, that means that this quotient space has a loop. When you have a loop, then in the bulk of ADS, the Witten instanton emerge. So Witten instanton is a very famous instability of flat space, where if you consider a flat space times S1, and if S1 direction breaks supersymmetry, then you can actually construct instanton in which this S1 shrink to a point in the bulk, and there is a hole of nothing in the middle of the Minkowski space, which expands at the speed of light and eat up the whole space. And exactly the same thing happens in the case of ADS. So this was known, and then after Qumran and I made a conjecture, we have received various suggestions from my colleagues that pointing out that they have construction of non-supersymmetric ADS. And all examples that I know of that have been informed to us has at least one massless particle which is marginal at the Breinton-Friedman band. So it's possible that a higher derivative term, a higher derivative correction can make it unstable. And so unless you check the coefficient of the first non-trivial higher derivative correction, it's very hard to see whether these are actually genuine counterexample or not. There was one very interesting example suggested by Haber, Riar, and Martin, and which is ADS5 class times CP3 in M theory. So this was constructed by Martin and Riar in 2008. And this is a very interesting example. So this is very similar to a Kachru-Silverstein example, but it turns, unlike this case, there is no pi 1 in CP3. So we try to see how this can be consistent with our conjecture. So fortunately, I had a very strong graduate student, Leo Spodinenko, and so we are looking at this, and we realize that there is actually non-trivial pi 2. So perhaps there is a generalization of Witten's instanton, where rather than S1 shrink to a point in the bulk, the S2 in this compactification shrink to a point in the bulk. And indeed, Leo, so I didn't do much. I suggested to Leo that maybe we can construct solution which is this S2 shrink to a point, and he constructed it, and so we wrote a paper. So this one actually turned out to be unstable too. So it seemed like almost all known example, except for the one that we still need to verify, check regarding the instability of some of the scalar field, seems to pass this test. And you can say that, well, even if it is unstable, maybe it has a finite lifetime. But it turns out that in ADS, any slightest hint of instability kills you immediately. The reason for this is the following. So if you have a flat space or antidata space, you can have a situation where you have some instability, you have a potential like that. But then if, for example, the tunneling, if the tunneling rate is small, then you do not worry too much, right? So you have other things to worry about. And but that is because the decay rate is what is this tunneling amplitude is giving you is a decay rate per unit volume. So if your space is big and you don't care because, for example, if the decay of vacuum happens million light years away, then it's going to take at least a million years for that to eat us. So we have other things to worry about in between. But in ADS, that's not the case. That if it is actually true that if instability happens with any finite lifetime, then it kills you instantly. The reason for this is the following. The causal structure of ADS is like this, where you have a boundary where you have CFT living, and you have Cauchy slice, right? So suppose vacuum decay happens over here. Then the light cone emerges from it and reaches the boundary in finite time. And in meantime, it eats you. But more seriously, the volume of this space is infinite. So therefore, the probability of anything happens here is actually infinite. Okay? So that means that this kind of decay happens any moment. Moreover, the volume actually diverges towards the boundary. So that means that probability of vacuum decay happening near the boundary is also infinite. Well, you can cut off the infinity by some cutoff scale, which is the same as introducing ultraviolet cutoff in CFT. But if you include cutoff, then actually decays happens with probability 1 in any instant near the boundary here. And that decay actually gets communicated to us by this light cone. So that means that the decay happens within the time of 1 over lambda, where lambda is a UV cutoff of conformal field theory. So that means that if you have ADS, which is unstable with any tiny decay rate like this, then it's going to kill conformal field theory instantly in the cutoff time of conformal field theory. So there is no such thing as unstable ADS. ADS has to be either absolutely stable or absolutely nothing. And so that's why when constructing non-supersymmetric ADS is a very risky business, that you need to check out that there is absolutely no instability mode. Okay? So that's the kind of things that we pointed out in this paper. And this has led to... Yes?
Sorry. Just a quick, it doesn't really matter for the conclusion, but as soon as you put in a cutoff, you do have to put in the actual time scale of the decay, right? So it's not, I mean, you have some finite volume, and so the rate at which the first bubble will appear.
So the decay time is 1 over lambda times exponential of gamma.
Yeah. So it might take longer than the cutoff time scale for the first decay to happen.
Well, so if you calculate, but lambda is a cutoff scale, right? So you want to take lambda to be bigger than anything that you have. It's a UV cutoff of CFT. So it's like a lattice.
But the decay rate is not an energy scale in any sense. I mean, I don't think you can compare those two numbers.
This is a number, but this is some finite number. You give me a theory, gamma is something you can
Let's just take the cutoff so that all you're left with is about 1 ADS volume in the bulk. Then it's very clear that you need to wait for a time of order e to the lambda.
Sorry, I'm sorry. How do you take gamma? What is your gamma?
So gamma is whatever the action is of some instanton, I guess, by which this decays?
Yeah. So this is something you can calculate in the smooth ADS. So this is, compared to lambda, it is something of order 1. You can take this, if you give me theory, I can calculate it in terms of this bulk potential and bulk gravitational scale. But lambda is something you want to take to infinity in the end of your calculation.
Then I certainly agree that you decay instantaneously.
Yeah, that's what I meant. So this is something you can calculate, and this is small but finite number in your theory. And then, but it's lambda is a cutoff scale. For example, in defining CFT, you can consider Ising model on a lattice, and you want to take lattice size to be 0 in the end of your calculation, and doing some scaling limit to go to conformal fixed point.
We're in complete agreement at the level of the equation that you wrote down.
Beg your pardon?
We're in complete agreement. I think I didn't agree with some words you said, but I agree with the equation.
Okay, thank you very much. Which part of my word did you maybe I should not. I have only like 5 minutes. So let's see, there are many other things I want. Oh, yeah. So there was another thing I wanted to tell you about, which is that this leads to, based on the work by Nima and the collaborator, some interesting speculation about the beyond standard model physics. So Nima and the collaborator pointed out a few years ago that if you start with standard model, just the standard model of a particle that is SU3 cross SU2 cross U1 over Z6, and then couple it to Einstein gravity, then if you compactify it on the circle to 3 dimensions, then depending on the mass and type of a neutrino, you can get de Sitter space, flat space, or anti-de Sitter space. And neutrino is relevant because if you compactify on a circle, and if you assume that in 4 dimensions you have some vacuum energy which is calculated based on this cosmic acceleration, then there is a Casimir energy contributing to the vacuum energy. And the neutrino is light particle, so that gives dominant contribution to Casimir. And so this leads to, but if you assume that there is no non-supersymmetric ADS, then it actually gives restriction on the mass and type of neutrino. Of course, there can be some beyond the standard model particles that can contribute to Casimir. So in that case, actually it gives a restriction on the type of beyond the standard model physics. So there has been some interesting work by a Madrid group and also a Madison group. And so this is another interesting development. And then there is a relation between weak gravity conjecture and the distance conjecture that people have been discussing, but I guess I don't have time to describe. For example, there is a generalization of weak gravity conjecture which is actually not completely understood. So I said that there is a generalization of weak gravity conjecture for P form. So in the case of P equal 0, it leads to some condition on instantons. And then it gets related to the distance conjecture in some ways, but it is still sort of work in progress. So in the final 1 minute, so I would like to mention something about this de Sitter conjecture. So this is a conjecture that Cameron and I suggested with our student George Obiet and Leo Spodinenko last year. And it was sort of generalized and refined in my collaboration with Eri Party, Gary Shu, and Qumran Baffa. And this is basically the generalization of what is called Dine-Zeiberg problem, which was suggested in 1985. So this is yet another property of scalar potential. So let me first point out, describe what Dine-Zeiberg problem was. So this was actually pointed out immediately after the first superstring revolution. So it was noted that in supersymmetric situation there are many massless scalar fields, and of course you want to stabilize it in order to be consistent with cosmology. And but they pointed out that you cannot find a stable point for scalar potential in the perturbative regime, that if you have a potential with scalar field, then the potential would always have this kind of runaway direction in the direction of weak coupling limit. And the idea is very simple. So you have a dilaton. So I take phi to be dilaton. And then if the dilaton is infinite, namely that string coupling constant is 0, then you have a free string theory, so in that case there is no potential. So the potential will be equal to 0. So then there will be a correction to this by finite string coupling. And it can be either perturbative, in which case you have g to the n, where with some finite positive integer n, or non-perturbative, in which case you have g to the n times e to the minus lambda over g to the k. So in either case, you can show that you see that there is an exponential decay of the potential in this direction. So you cannot create something like that in sort of perturbative regime. And in fact, asymptotically, in this case, the derivative of the scalar field with respect to the potential goes like this, where C is of order 1. So Qumran and I, in collaboration with our friends, speculated the possibility that this can be more general. That not only this is true in the case of dilaton, where dilaton goes to infinity, but can be true for any direction in the scalar field space. But in that case, actually, in order to avoid some of the counterexample and also give some justification to the argument, we needed to formulate it so that you have one more condition. And so if you give me maybe 5 minutes, I would like to describe what motivates us to do that. So suppose you have a scalar field with potential. So suppose, for definiteness, let me just consider a case when the vacuum value is positive. So in that case, if you have a positive vacuum energy, you can start, a universe can start accelerating. But in fact, if the gradient is too small, it's going to drive the kinetic term for the scalar field so that you don't get accelerating expansion. So what happens is that if the derivative of the potential is less than square root of 2 times v, then you have accelerating universe. The universe with positive acceleration in its expansion. But this is actually not sufficient for the accelerating expansion of the universe, because if there is actually vacuum fluctuation which becomes too large, then this is actually not allowed. So for example, if you have a tachyonic direction, and if the tachyonic direction is too strong, then you can have a 0-point fluctuation at the horizon crossing, which can become tachyonic. So in order to avoid that, you would like the smallest eigenvalue of the Hessian to be bigger than some number times potential. So if these two conditions are satisfied, then you can have accelerating universe with semi-classical description. And if you have an accelerating universe with semi-classical description, then you can actually, this leads to some puzzle. Because if you have an accelerating universe, then there is a thing called Bussow bound. And so the idea is that if you have a region in space, and if you have a light sheet which ends in caustic, then you can actually bound the number of states which crosses this light sheet by some geometric formula. Raphael can correct me if I'm mistaken about the use of his conjecture. So if you have an accelerating universe, then you can apply this to apparent horizon. Apparent horizon is the following thing, that if you have an apparent horizon, you have a light cone which points both in the interior region. This is a local condition, so this may not be cosmic horizon, but if there were a cosmic horizon, it's always outside of the apparent horizon. Apparent horizon is always inside of the cosmic horizon, which means that this light sheet always ends in some caustics. So then you can apply Bussow bound, which means that the state inside of this region, that the dimension of the Hilbert space of this region is bounded by exponential of one of the potential. So I'm just running out of time, so I cannot complete the logic. But our argument was that this is actually in tension with the distance conjecture. that if the distance conjecture says that if you go in a scalar field space for distance greater than Planck scale, then you start getting light degrees of freedom. But if you start getting light degrees of freedom, then you can start creating lots of states in the Hilbert space. So this is very similar in spirit to species bounds, but applied in slightly different way, so that it doesn't lead to similar kind of issue. But then you start getting some tension with this upper bound of this. So this leads to the formulation of our conjecture that either this opposite inequality is true, or this inequality must be true. So in that asymptotic region, and then we can discuss various consequences of this, but let me leave this to the discussion session, and thank you for your attention.
Thank you very much, Hiroshi, for your very beautiful lectures. Are there quick questions for now? You will still be here in the evening?
Sorry?
You will still be here for the discussion
I'll be here for the discussion session and take any questions.
Very good.
I cannot promise I will answer all the questions, but try.
Then we will postpone the discussion till then, and we reconvene at 11 o'clock. Thanks again very much, Hiroshi.